Hello everyone, I'm Norman Wright, a product manager at METTLER TOLEDO AutoChem. Thanks for joining our presentation today, in which we will discuss the value of using Raman Spectroscopy in a METTLER TOLEDO workstation for polymerization reaction studies. As a vibrational spectroscopy, Raman provides unique spectral information for any compound with a carbon skeleton and functional groups. Today, we will perform a straightforward reaction in which we create a polymer from the starting materials of ethylene glycol and phthalic anhydride in a condensation polymerization. During the reaction, we will track the carbonyl bands in the anhydride ring of phthalic anhydride, first seen at the initiation step, and follow its depletion, and of the formation and growth of the ester group, indicating that a new polymer has formed. In addition, we are using an EasyMax 402 to control the temperature of the reaction, and with iControl software, synchronize the temperature program with the Raman data collection and reporting. This is an easy way to simplify your work effort. Now, I'll turn it over to Sid to discuss the setup.
Hi everyone, my name is Sid Raizada, and I'm a chemical engineer here at METTLER TOLEDO AutoChem. What we have here is a reaction monitoring platform for our polymerization experiment. The ReactRaman 802L is the main instrument we plan to demonstrate today, but we are also using the EasyMax 402 automated workstation for this chemical reaction. EasyMax is a thermostat that provides control of the temperature in the system from -40 to 180 degrees Celsius. Traditional round-bottom flasks and jacketed lab reactors require manual control of parameters, such as temperature or mixing, which can be time-consuming to set up and cause challenges with experiment repeatability. The EasyMax allows for easy control of critical process parameters, either through the user-friendly touchscreen or by laptop with the iControl software. Using the touchscreen, you can interactively control the temperature and the stirring in the vessel, as well as create a task with up to 6 steps. For more sophisticated recipes, you can use iControl software, which has an unlimited number of steps and can run repeated experiments unattended. This facilitates automated data capture as well. Parameters such as stir rate and temperature are recorded and captured as the reaction progresses. For this polymerization, we are using a 2-piece 400 milliliter vessel with a PTFE lid, overhead stirrer, and temperature sensor. Alternatively, you could use the single-piece reactor vessel, such as the one in the second position, with a glass stirrer, used for air-sensitive and moisture-sensitive chemistry. The ReactRaman works with the EasyMax for ease of use in-situ monitoring of reaction kinetics, intermediates, and endpoints throughout the experiment duration. Users can choose the excitation power of the ReactRaman for the highest data quality and validity. Cosmic ray removal is also enabled by default, which removes any cosmic ray spikes from the data and allows the user to only focus on the changes that are relevant to the reaction. The system contains a Class 3B laser that has an excitation wavelength of 785 nanometers, and the probe shown here, which is a standard immersion probe of 9.5 millimeters in diameter, is made of C22 Hastelloy with a sapphire window and a gold seal at the probe tip, and can handle temperatures between -40 to 300 degrees Celsius. The orientation of the ReactRaman doesn't affect the performance, so it can be placed on a bench or placed vertically. The ReactRaman has 5 safety interlocks that must be checked and engaged before the laser is projected. If any of those safety checkpoints fail or are disengaged, the laser will turn off automatically. The probe is connected to the base unit with a fiber conduit and a Smart Connect probe head assembly that is used to easily switch out sampling technologies. Other sampling technology options are the extended immersion probe, short working distance probe, flow cell optic, and non-contact optic. This probe-based instrument is directly immersed into the reactor vessel. and begins providing real-time spectral information on the reaction species present in the solution. This probe does not require sampling preparation and delivers data immediately as the reaction progresses. Fit for purpose, ReactRaman 8.0 software is used to operate the instrument, collect real-time spectra, and analyze the resulting data. Now, I'll be handing it off to Norman for experiment preparation, data collection, and analysis.
Thank you, Sid. Before we get started with the experimental setup, I'd like to talk about the software programs that are going to run the experiments today. The first one, iControl, that will be controlling the EasyMax and setting the temperature profiles for the experiment, and also ReactRaman that'll collect the data that we will be looking at a little bit later in greater detail. First, I'd like to look at the PC screens for the two programs that we're going to be looking at today. Up on the screen right now is iControl, and iControl has a program set on the left-hand side for heating the reactor and of the EasyMax and also stirring the reaction as we progress. On the right-hand side, it shows the things that are attached to it, the EasyMax, the reactor 1, in which we'll be doing the reaction, and the ReactRaman. To get started in the experiment, we'll simply click the Start button here on the top taskbar, opening up a screen to remind us to go to ReactRaman and set up the parameters there. As we see this page pop up on the Quick Start menu, the name of the experiment is set in here already. I'll pre-set in, but it has the time and a date stamp, so that'll be unique to an experiment if you don't add additional information to the name, the folder where the experiment is going to live. And right now, the duration of the experiment, we'll call it 1 hour. And we're going to collect data with a sample interval of 30 seconds. So I'll now create the experiment. Get rid of a couple of these warning screens. And one thing we want to do now is to optimize the exposure time that we need for the reaction. Since we have the major solvent material for the reaction in the reactor now, I'll just simply hit Quick Optimize. It will go out. It will look for the highest signal within the spectrum, and it will calculate an exposure time from that. It came back with an exposure time of 0.7 seconds, so that sounds about right. It will put the highest band somewhere around 50%, 60%, and now we're ready to go. It's holding now. We'll quickly go back to iControl, and we will hit Start Experiment. Everything goes green at the top, showing that it's running. And there's green bars down on the bottom taskbar showing that the Raman is running as well. We'll check in on the Raman in a moment. So we can see now that we're stirring. Turned it on to 350 RPM. And now we're waiting for a minute to make sure everything is stable before we start our heating cycle. I'll now go over to Raman, and we are collecting data. The first spectra is probably showing right here, ethylene glycol, a spectrum of ethylene glycol. Okay, and that's what we'll be looking at now for the next several collects to get a stable, sort of a baseline for where we're starting our experiment. We may want to use that later in data analysis, but we want to make sure that the Raman is running, it's collecting data. We know that the sample is stable. The spectra should be repeatable. So here we have two spectra collected and displaying in the surface plots. On the right-hand side, we have a trends line. Again, the trend is looking at the saturation level, and it should be changing very slightly at the beginning where there's no temperature changed. Later, as we start to heat, it'll drop. Right now, we have three spectra collected. As we're looking at two screens, we have the potential of flipping back and looking at the spectrum again, but this is the latest one collected. So we don't get a good perspective on if there's any changing going on as we progress through the experiment. Really the interesting information will come in from this surface view and the trends line. So we'll have those two up, and I want to pull this one back onto the screen just a little bit. And we will wait. We'll go into sort of a waiting mode for about 10 minutes until we're ready to we are at temperature so that we can add the remaining components of the reaction material, and then we'll start looking at the reaction at that point. All right, we're back from our break. The reactor is at temperature, and now back to Sid for the next part of the reaction.
Yeah, so as Norman mentioned, we have now heated up our ethylene glycol solution to 60 degrees Celsius and also waited a couple minutes as per the iControl recipe. Now that we've had that solution reach the set temperature, we're going to be manually adding in 20 grams of phthalic anhydride and 0.8 grams of sodium acetate.
Great. Okay, thanks, Sid. Now back to our Raman spectra, and we will look at the changes now that have occurred, first looking at the surface plots. And let me zoom in a little bit to this section right in here, where we can first see a drop in the intensity of the ethylene glycol. And then we're starting to see some peaks grow up here from the addition of the other materials. Over here in the spectral plot, which I'm going to expand a little bit, we can see the difference between before and after, with the black trace being the after, so we can see the changes from after the addition of the second materials. So now we can start to look at the changes. And what I'm going to do is I'm going to zoom a little bit more. So we can use the zoom bar here up on the top to look in at those peaks right there. And just I'm going to click on this one here. And over here in the spectrum, on the spectral view, I can click on this, and it says right here it's 1848 wave numbers. And so what I'm going to do is I'm going to click on peaks down here below. I'm going to add a new peak. They'll come in at that 1849 using a height measurement and a baseline to correction to a 2-point baseline. We're looking at the peak at 849. We've added it to the trend line. And now we'll add in a second peak to monitor, which is at 1721. So it's this one right here. And then we'll look at the changes in those two bands for the reactants going up and being used up during the reaction. So I'll add that new peak. Same, making it a peak measurement. And we'll do a correction from 2-point from baseline. I'll drag that down on both sides like this. We have our baseline selected and we have our peak max selected. So that'll give us a value to monitor. I'll go back and I'll look at the 849 peak just to make sure that I've got it set correctly. I'll scan over slightly. Okay, I didn't get the baseline set correctly, but I will do that now. So I'll pull that down and I'll pull the other one down over here. And then we can expand our region here if we are going to change to, for example, an area measurement rather than a peak height. So we define the regions we're working with for these two bands, and now we can zoom out a little bit more to see how the rest of the reaction is going. But this is where we have some primary bands of interest. Now, going back to our view of the trend lines, what we can look at now after we added the reaction material, we have peaks at the 1849, the 1721, and the saturation level. I'm going to take the saturation level out of the view for simplicity's sake, and then we'll simply watch the change of the original material in gold dropping down while the product is now rising up. So as time passes, and we're going to be collecting data now, we will see that complete. So we'll see the reactant drop off. We'll see one grow in, one drop off. A pretty classic type of reaction. So we'll just keep these two views up and we'll watch them a little bit longer, and then we'll be done. Now that we have collected data from the experiment, let's take a look at how we can extract important information from that data set. We'll go back to the data screen on the computer for that. Okay, here on the screen we have the full data set from our experiment. On the surface plot to the left, we can look at a couple of features just in general. At the beginning, the ethylene glycol dropped in intensity with the increasing temperature as we heated it up for the reaction to begin. And then as we look at the very bottom here, we can see the pieces that are growing in. And I'll zoom back into that. We did that during the collection of the data, but I'll go back into it. As we look on the right-hand side at the top, the trend lines, remember that we added peaks during the reaction at 1849 wave numbers and 1721 1721. So they're still here in gold and in blue. Since then, we've dragged in the temperature profile from eye control for the EasyMax, so we can watch the heating of the reactor to get to the point where we wanted to actually start the experiment, and that's the dotted red line here. Once we arrived at 60 degrees, we dosed the experiment to get it started, and the interesting things happened at that point on. Okay, so now what I'm going to do is go back to the surface plot and zoom in a little bit more. Well, first I'm going to look at this and say, is there anything we want to improve about this data so that we can extract the information that we want? And a couple of things that we always take a look at for Raman is, are there any scattering effects that we see during the data collection? And for that, if we want to take a look, we can look at scattering corrections. We have a pull down here. We can do an SNV and see if that pulls it down. It didn't appear to do anything in particular because we have a pretty well-behaved baseline, as I zoom out a little bit here to show. The other thing that we can look at is, while I remove that scattering correction, is a baseline correction. We have an active baseline correction program unique to the ReactRaman program. And if I click on it, it will give us a little bit of improvement in the baseline features. So we have our bands of interest going near zero, and that's the way we'd really like to look at it. So I'll leave that baseline correction on. Now I want to zoom out a little bit more to where we were looking for our bands at 1721 and 1849. And so they are sitting right in here. And what we can see from the surface plot, again, is the ethylene glycol is here on the left. It peaks out in a little bit of yellow, and it's constant. It's providing one of the components of the reaction. The phthalic anhydride that we add is initially going in, and then it drops back off. That's the peak at 1849. And the peak at 1721 that I'm looking at right here grows in. So this is the product of the reaction. So we had the original material that we're using that's in excess. The ethylene glycol, we have the phthalic anhydride that we're putting in that will be used up, and then the product that's formed here that's growing in. So as we look at our trend line, we can see, one disappearing essentially. We're adding it, and then it reacts and drops away. The product grows in at basically the same time. We get to a steady state, and we really know that the reaction is over. Well, in this case, about 45 minutes in. Let's look at the peak values. If I click on that peak and I select a band out further into the reaction stream. So if we look at the spectra, we can select and pin from the Home tab a reaction, a time experiment that is towards the end, and we'll grab that. We can grab one that's up near the beginning when we added the phthalic anhydride, and I can pin that. And then one that's way back here at the beginning, that's the ethylene glycol, and I'll pin that. So we have kind of the three different pieces of it. If we look now in our spectral window, we can see three different components here. The ethylene glycol is always constant here, about 1450. And then as we get up into the blue, we see the product growing in, and in green we see the phthalic anhydride as it begins the reaction, and then it fades away. So if I click on that, we can look over here in our surface plot, and we can tilt it a little bit, and in time we can see it fading away. At the same time, if we look at the band at 1721, this is our polymer product growing in, our polyester product that grows in as our phthalic anhydride is used up in the reaction. So we have these three different locations. We can see it in the spectral files, and we can watch it in the trend files up here. So from this, we have immediately been able to look at the differences in the spectra, and the time-base spectra gives us an easy look at what's happening, and then we can translate that into the trend line so that simply without thinking about spectra, we can just observe what we know about each of the components, the ones that are added and used up, and the ones that grow in during the reaction. One of the materials is disappearing as it reacts and forms the second material. And so this is really the essence of this simple polymerization experiment and the details on how simple it is to get this information from ReactRaman data. I hope you found this session useful today using the reaction workstation configured with EasyMax 402 and ReactRaman. We have shown the steps needed to collect quality data from a polymerization reaction using IC Suite software, iControl to operate the EasyMax, and ReactRaman to collect and process the data from ReactRaman. Both are designed for simple but powerful operation with intuitive steps to extract the answers you need from a reaction. We will now take questions, but of course, please reach out to METTLER TOLEDO for a more complete discussion regarding your workplace needs, and especially to follow up on this presentation. Thank you.